In this lecture, we'll consider linear equations with two variables. For example, consider the two equations 2x plus y equals 5 and x plus 2y equals 4. Find the values of x and y such that these two equations are both satisfied. If we play around with the numbers, it's not that hard to see that x equals 2 and y equals 1, and that satisfies both equations. But how do we get those numbers without guessing? First, there are two algebraic methods to solving these equations. We'll begin with the first technique. To keep the explanation as clear as possible, we'll write these equations one on top of another to keep track of the numbers. 2x plus y equals 5 and x plus 2y equals 4. Remember that whenever we have an equation, we can perform the same operation on both sides without changing the equation. What we want here is for the equations to have opposite terms. If the top one has a 2x, we'd like the bottom one to have a negative 2x. That will allow us to cancel out the x variable, as we'll see in a minute. The way we can do that is we can multiply the bottom equation by negative 2. That is, multiplying negative 2 by all the terms in the bottom equation. Since negative 2 times all the terms in the bottom of the equation give you negative 2x minus 4y equals negative 8, we're left with the following. The top equation is still 2x plus y equals 5, and the bottom equation is negative 2x minus 4y equals negative 8. Now we can add the two equations together. We can do this because we're adding equal quantities, and so we're not changing the equal symbol. If we add both, what we get is 2x plus y minus 2x minus 4y equals 5 minus 8. The x's wipe out, and it simplifies to negative 3y equals negative 3. By multiplying the whole bottom equation by negative 2, we were able to establish it so that the variable x would cancel out when we added the two equations together. What we're left is negative 3y equals negative 3, and if we solve it by dividing each side by negative 3, we get y equals 1. We've now established that y equals 1. To get the x value, simply substitute y equals 1 into any one of these equations. Say the first one, 2x plus y equals 5. So 2x plus 1 equals 5. This solves easily to x equals 2. So we've obtained the solutions, x equals 2 and y equals 1, without guessing. Let's look at another example. Solve 3x plus 4y equals negative 11 and 5x minus 2y equals 25. As before, let's write these equations on top of each other to make it easier. 3x plus 4y equals negative 11, 5x minus 2y equals 25. Now, we have to figure out a way to get it so that the equations are going to cancel one of the variables when we add them to each other. The easiest target seems to be the y term. We can multiply the bottom equation by 2 in order to get the y term to be negative 4y, which will cancel out with the 4y in the top equation when we add them together. Multiplying everything by 2 in the bottom of the equation makes the bottom equation 10x minus 4y equals 50. So we're left with the following two equations. 3x plus 4y equals negative 11, and 10x minus 4y equals 50. Add the two equations together, and you end up with 13x, the y column gets wiped out, equals 39. Divide each side by 13, and the solution to the equation is x equals 3. To get y, just substitute x equals 3 into either equation. Say the first one. So you get 3 times x, which is 9, plus 4y equals negative 11. Subtract 9 from each side, and you have 4y equals negative 20, which computes to y equals negative 5. Thus, we've solved this equation as x equals 3 and y equals negative 5. A third example. Solve 2x minus 3y equals negative 6, and 3x plus 2y equals 4. This is a bit trickier than the other ones. We can't multiply the first equation or the second equation by some number to get a new equation whose coefficients will automatically cancel each other out if we add the equations together. What we can do is strategize a little bit and multiply both equations by some number so that one of the variables will cancel out when we add them together. In this case, we can do that by multiplying the first equation by 2 and the second equation by 3. Multiplying the first equation by 2, multiplying 2x minus 3y equals negative 6 by 2, gives us 4x minus 6y equals negative 12. Multiplying the second equation by 3 gets us 9x plus 6y equals 12. In this case, when we add the two equations together, the y's cancel. 4x plus 9x is 13x, and negative 12 plus 12 is 0, which means that our answer is x equals 0. Substitute 0 for x into either equation, say the first one, and we get negative 3y equals negative 6, so that y equals 2. So our solution is x equals 0 and y equals 2. It should be noted that there are different ways of multiplying equations to isolate one variable by itself. The solutions we presented are not necessarily the only way of doing it. If you manage to find another approach, you can use it as well. This method works as long as you are eliminating one of the variables when you add them together, and therefore this is known as the elimination method. The next method is what we call the substitution method. This is where you solve both equations by getting what one of the variables is in terms of the other by one of the equations. The procedure goes as follows. We're going to solve for one of the variables in terms of the other and then substitute it back into the original equation. Let's look at an example, because in the abstract it's hard to figure out what that means. Solve the equations 2x plus y equals 5 and x plus 2y equals 4. Now, we solved these already before using the elimination method, but let's use the substitution method now. Pick one of these two equations, doesn't matter which one, let's say the first one, 2x plus y equals 5, and solve for one variable. It's easier to solve for y because it has no coefficient. In the equation 2x plus y equals 5, we can solve for y by subtracting 2x from each side, yielding y equals 5 minus 2x. Now take this equation and substitute it in the second equation. The second equation was x plus 2y equals 4. Now, we know that y equals 5 minus 2x. So if we just substitute 5 minus 2x for y, we get the equation x plus 2 times 5 minus 2x equals 4. Opening up the parentheses using the distribution method, this simplifies to x plus 10 minus 4x equals 4. And combining the x's gives you 10 minus 3x equals 4. This is a linear equation and easy to solve. Subtract 10 from each side, getting negative 3x equals negative 6. Divide each side by negative 3, and we get that x equals 2. Take the x equals 2 and go and apply it to either equation before, and you'll quickly see that y equals 1 in either equation. That's our answer, x equals 2 and y equals 1. Let's take another example. We'll solve the system of equations 4x plus 2y equals 10 and x plus y equals 1. We could do this almost as easily using the elimination method, but we will use substitution. And we can do that by solving for x in the bottom of the equation. We could also do it for solving for y, but we'll do it for x, just why not? If we subtract y from each side, we get x equals 1 minus y. We can then take that 1 minus y, which we now know is equal to x, and substitute it for x in the top equation. So instead of 4x plus 2y equals 10, we can get 4 times 1 minus y plus 2y equals 10. That expands to 4 minus 4y plus 2y equals 10. Combine the y's and we have 4 minus 2y equals 10. Subtract 4 from each side and we have negative 2y equals 6. And then divide each side by negative 2 and you have y equals negative 3. To figure out what x is, go back and apply it to either equation. If you do it with either equation, you will see that x has to equal 4. So our solution here is x is 4 and y is negative 3. The final method of solving a pair of linear equations is the most elegant of all. It's very geometric. We simply graph the two equations on a Cartesian plane and look and see where they intersect. To illustrate this method, suppose we want to solve 3x plus 4y equals negative 11 and 5x minus 2y equals 25. We looked at this equation earlier and solved it using the elimination method. We graph each equation and see where they intersect. What kind of graph are these? Well, these are both going to be linear equations, and so therefore the graph for both are going to be straight lines. To graph each one, we simply have to pick a value for either x or y, and then figure out what the other is based on that, and then we have a point. Do that with any 2 points, draw the straight line that intersects with both points, and you've graphed the equation. Let's graph the 3x plus 4y equals negative 11. We just need 2 points. So let's first pick y equals 1. Why not? If we do, then we get 3x plus 4 times 1 equals negative 11. Subtract the 4 from each side, and we have 3x equals negative 15, and x turns out to be negative 5. So our first point is negative 5, 1. Then let's pick where y is negative 2. In that case, we have 3x minus 8 equals negative 11. Add h to each side, and you have 3x equals negative 3, or x equals 1. Our point in this case is negative 1, negative 2. So we have a line where one point is negative 5, 1, and another point is negative 1, negative 2. We could have picked any value for x or any value for y, and we would get a point on this line. We just plot these points and connect them with a straight line. Now let's graph the second equation. 5x minus 2y equals 25, and let's say that y equals 0. If y equals 0, we wipe out the middle term, and we have 5x equals 25, and x is 5. So 5, 0 is 1 point on that equation. Let's then turn to x equals 7. If x equals 7, then it would be 35 minus 2y equals 25. Subtract 35 from each side, and we have negative 2y equals negative 10. Divide each side by negative 2, and y equals 5. So 7, 5 would be another point on this line. We can plot these 2 points and connect them with a straight line. The remaining step is to have both on the same pair of axes on the same Cartesian plane and see where they crisscross, see where they intersect. If we draw these 2 lines on the same Cartesian plane, we can see that the 2 lines intersect at point 3, negative 5, which means that our solution is x equals 3 and y equals negative 5. Note that we could have picked any values for x or y on any graph, and we would have gotten the same result. Second, even though this method is more elegant than the first two, it has some drawbacks. Graphing is time-consuming, pictures need to be drawn carefully, and you may need graphing paper. And even if you do draw everything carefully, the point of intersection does not necessarily occur on a line, which means that the coordinates might be fractions or decimals, which are very hard to indicate when you're talking about looking at them on a graph. For this reason, the standard method for solving two linear equations is either by elimination or substitution. The graphical approach is useful for giving us insight as to the nature of the solutions to these equations, but the computations are usually done by one of the other two methods. Now let's apply this method to a word problem. Let's say there are a total of 25 coins consisting of quarters and dimes. The total amount of money is $4, or 400 cents. How many quarters and dimes are there? Well, what we can do is say, let x equal the number of quarters and y equal the number of dimes. Just because we know that there are 25 altogether doesn't inherently mean that we know how many of them are quarters and how many of them are dimes. However, we can also establish another algebraic relationship by saying the total amount of money is $4, or 400 cents. The first algebraic equation, the first expression, would be expressed by x plus y equals 25, because the number of quarters and the number of dimes sum up to 25. Since each quarter is 25 cents, if there are x quarters, we have a total of 25x cents. Similarly, since each dime is worth 10 cents, if we have y dimes, then there's a total of 10y cents. For every dime is 10 cents. The total amount of money is 400 cents. Thus, we can establish a second algebraic equation of 25x plus 10y equals 400. So we have two linear equations, x plus y equals 25, and 25x plus 10 equals 400. We can use substitution or elimination, and of course there are many individual ways to do each one. For purposes of simplicity, I'm going to use elimination. And the way I'm going to do that is to multiply the top equation by negative 10 so that the middle term can cancel out when we add them to each other. If we multiply the entire top equation by negative 10, we get negative 10x minus 10y equals negative 250. Now we add the equations together. 25x minus 10x is 15x. The y's cancel, and 400 minus 250 is 150. So we have 15x equals 150, which simplifies to x equals 10. If x is 10, using the top equation, it's very easy to see that y has to equal 15. And in fact, if you check it, you will see that it's correct. The 10 dimes are $2.50, the 10 quarters are $2.50, and the 15 dimes are $1.50, totaling $4. In this lecture, we learned how to solve two linear equations together. In the next one, we're going to also have two equations, but that one of them is a quadratic equation, and see how when you have multiple quadratic equations, or a linear and a quadratic, you might have 0 solutions, 1 solution, or even 2.